Hello, everyone. So today we're going to talk about ByzRP, which is our take on how to recontextualize a little bit the RPKI infrastructure. And before we go into the actual details of the ByzRP infrastructure that we developed, I have to quickly take you through a little bit of a introduction as to what RPKI exactly is and how our solution fits into the whole ecosystem of Internet security. So it all begins with BGP, the Border Gateway Protocol. This is one of the core protocols of the Internet, but because it's so fundamental and was developed so long ago, it has several shortcomings. So as BGP was developed in the early 90s, the priorities during its design were things like scalability, efficiency, speed, but not security. And the consequences of that is that today, BGP attacks, also called hijacking attacks, they are very common. They happen quite often, and they always come with a pretty hefty price tag for the victims. So how a BGP hijack would work go something like this. Let's say Autonomous System 1 is the rightful owner of prefix 1230/24, and this autonomous system, the routers in this system are going to send BGP announcements out there saying that, hey, I am the actual owner of this prefix, so if you want to contact anyone in this prefix space, you need to send the packets to me, AS1. And eventually, those who received this announcement, in this case AS2, it's going to propagate this announcement further. Some router out there is going to get another forward announcement that says, hey, if you want to reach 1230/24, you have to send the packet to me, AS2, and then I'm going to forward it to AS1, the actual place where this prefix is located. So far, so good. The problem is that routers make their decisions using a very neutral heuristic, meaning that they don't take into account security at all. They don't have any parameters for that. So a malicious actor can enter the ecosystem, send a conflicting announcement as to where the location of this prefix is, and because in this particular case, the malicious autonomous system has a shorter path than the real one, than the benign one, that's the one that's going to get chosen by the router, and therefore we have a case of a hijacking attack, meaning the packets are not going to go to the correct destination. And this is actually, might seem quite simplistic, but quite often this is really where it all ends up in terms of BGP hijacking attacks. Sometimes it's just the shortest path that makes the difference. And the routers have no way of telling which is valid and which isn't. So the RPKI is the solution that was introduced to mitigate this problem. There have been many solutions over the years, but RPKI truly is the one that it's taking, it's becoming the most widely deployed one on the internet right now. So how the RPKI works goes in the following way. So we talked earlier that the purpose is to protect the origin of the packet so that they go to the correct destination. And for that, the owners of prefixes, they need to create a cryptographically signed binding between a network prefix and the autonomous system number that's supposed to be their source. And then they store this into repositories called publication points, which are spread all over the internet. And they're stored there, and they are cryptographically signed, so you can verify their origin and verify that these are valid delegations. Now, if anyone wants to protect their infrastructure using the RPKI protocol as a whole, they have to install the relaying party, which is, or the RP here in the figure, which is the software engine that essentially collects all of this data, all of these tuples, does the validation that the data in these repositories is actually correct and I can enforce that, produces the output by validating those tuples, and essentially sends this output to the router. And what the router at the end of the day gets is just a list of tuples, prefix and autonomous system number, bindings that were verified to be valid. So at this point in time, when the router receives this data, now it has a ground truth. It has a ground truth with which it can evaluate BGP announcements, whether they are valid or whether they are potential hijacking attacks. And RPKI has gotten a lot of popular in the past couple of years. Major companies, virtually, if not all, tier 1 ISP providers enforce RPKI. Major IXPs enforce it. Major companies like Amazon use it to protect their resources. So it's really is becoming the status quo to protect from hijacking attacks. And it's gotten so popular that even the FCC, and followed by the US White House just last year, published roadmaps for securing internet security in the United States. And in these roadmaps, RPKI was very prominently featured as something that could even become enforced at some point in time by legislation or by requirements to participate in government contracting. For those who want to actually have deals with the government, they have to make sure that they are doing everything possible to protect their resources. So keeping this in mind, how popular this protocol is becoming and how maybe it might even verge on becoming something that would be legally enforced at some point, we came to the idea that since we've been studying RPKI for a long period of time, we know of some shortcomings of the current infrastructure as RPKI is deployed, is currently implemented. And we designed ByzRP as a retake on how this infrastructure could look like to make it all better, safer, and maybe even more robust than it currently is. So the first problem that faces the RPKI is the advent of malicious publication points. This is quite a feasible type of compromise that can happen. So this here is a simplified representation of how the RPKI looks like. Publication points, you have a relaying party that is the middleman between this publication point data and the routers, and this relaying party is the one that collects all the data. But let's say that one of these publication points is malicious, and what it can do is it can instantiate a stalling attack. And what the stalling attack essentially does is it slows down the RPs for many hours, so much that some data in its cache expire. And the consequences of that is that if data is expiring, some of the output is no longer going to be correctly evaluated because the expired file, that binding is no longer valid, it's no longer going to be sent to the router. And therefore the router is going to have a limited view of the ground truth that we spoke about earlier. So for more details on how stalling attacks operate, our team also had a Black Hat talk in 2022. It's online. You can check that out for how a stalling attack would work. Another type of attack is, good old DOS attack, crashing the relaying party. And this is, again, something that is quite feasible to do. It's really not that difficult. The entry barrier to become a publication point is also not that high. It's not too expensive. It's not technologically challenging. It's quite feasible for a malicious entities to enter this RPKI tree of repositories. And they can have bad files that can cause crashes. And because of how the relaying parties work in and of themselves, these crashes can create a situation where the relaying parties are no longer producing any kind of output for the routers. So now the routers are fully RPKI downgraded and there is no ground truth anymore. Also, for more information on the characteristics of DOS attacks on routers, we also had a talk last year. But safe to say, when we did the measurements last year, we found that at least 50% of all relaying parties currently being used on the internet are actually vulnerable to DOS attacks for various reasons, from processing issues to outdated implementations. So this is really an attack vector that is out there and can be exploited at any time. So what can we do to solve this problem? In terms of protecting the RPKI infrastructure or the relaying party from these types of attacks, what we decided to do was to create a watchdog. And the purpose of this watchdog is to do what the RP doesn't do, security monitoring of the processing. And what the watchdog very specifically does is it monitors the well-being and the health of the relaying party itself. Is it operating correctly? Has it crashed? Check what's going on there, and monitor the health of the connections the relaying parties establish with publication points. And if the watchdog sees any type of anomaly, a connection that is lasting too long, or a connection caused a crash in the relaying party, it's going to add that publication point that is on the other end of this connection to a skip list, and then reboot the relaying party. And after the relaying party is rebooted, it's going to be skipping the maliciously operating publication point. This here is a a simulation that we did of a DOS attack and how our system behaves under these circumstances. So the most important thing to keep in mind here is this purple line over here. The purple line is the output of the infrastructure that we have, so the number of VRPs, the number of tuple autonomous system number bindings that are put out for the routers out there. And in the y-axis, this is just the number of these bindings that are there to be offered to the routers. So what we see here is that it takes a little while for the system to warm up. We'll talk about that a little later. And then eventually it goes up to the maximum number of bindings that are possible. At the time of these measurements, it was 517,000 bindings out there, so VRPs out there. And the way the simulation worked is the following. The system was supposed to work normally for like 15 minutes, and then after 15 minutes, we simulate a crash for a particular publication point. And we see here that after 15 minutes, we see a drop in the number of VRPs. The drop is the result of the fact that the publication point that is causing the crash is not going to have its data processed anymore because it's going to be incomplete data. So that data is going to be invisible to the output, but everything else is going to continue to be correctly processed and correctly served. So as we see here, there is no operational downtime. If this was a normal relay part, this line would have just gone down to 0 and it would have never gone back up unless someone or some operator had manually gone into the system and tried to bypass the malicious publication points, because the relaying party have no security mechanisms built inside of them by default. Another thing that we observed was the fact that, as we were doing these different measurements for how RPKI operates, we were seeing that there was a lot of instability when it came to networks, and there was a lot of instability when it came to the output. So this is the simplified representation of RPKI that we saw earlier. This is still, despite not looking very simple, still quite a simplified representation of the RPKI environment. So what we did was we put relaying parties in different networks, into different hosts, different VMs, different containers, and we let them run. Some in parallel, so in different networks, but in parallel. Some, they were staggered runnings, and we checked the output. And what we saw in the output is that it wasn't constant, it wasn't stable. And it wasn't like the bindings were going up, so we can say, oh, there is growth, therefore when I check again the data, there's more data. It was plus 13, minus 50, plus 300, minus 500. It was really an oscillated, there was a lot of oscillations in the output. It wasn't really stable. And the same thing would happen even if I had one relaying party on one machine and I was running it sequentially every 10 minutes, every 15 minutes, the final output would be different numbers. At various points in times, this would happen quite often. And we checked into the logs as to what exactly was happening here. And our ideas of what we got out of what we studied was that this wasn't some kind of systemic error out there, but this was more the result of network instability, repository instability, connection drops. We saw many times some of our relay parties were quite literally unable to establish connections with publication points at some points in time because they were just so overwhelmed with connections that they just couldn't accommodate us as well. But at a later point, they were able to establish that connection. We saw that sometimes the connections would just drop. They were established. They would just drop. Often, what happens quite often is also the content itself is oscillating, so it's changing because people are updating the files, they're adding new data, they're deleting data, so the snapshot view that one single relaying party sees is not quite comprehensive. It's not quite final yet. So we would have this would be like the tableau that we have. And if we focus here on this part with the output, what's between the relaying party and the router, you will see that the consequences of this instability is essentially that depending on where you put your relaying party and depending on at what point in time this relaying party is establishing a connection, it would have a slightly different output. They would all have a slightly different output from each other. And all of these routers that are being fed by these separate relaying parties, they're ultimately going to be having, to be receiving not the same data, a ground truth that is slightly different from each other. This is not exactly what you will want to have from a security system, that every single receiver of this security relevant information gets disparate data points. some uniformity is also a desired state. So our approach to bypass these problems was the following. So we had this enhanced version of the relaying party from the previous slide. We have the relaying party and the watchdog. And so what we did is we deployed this relaying party and this watchdog on different containers and different hosts out there. And we let them all run in parallel. They are all completely independent from one another. They do not influence each other. And they all come to some kind of output, each of them. And after they reach the output that they have, we aggregate the results for each of these relaying parties. We aggregate these results using the majority voting. And then what we have here is a situation where we have nodes that are resistant to attacks, DOS or stalling attacks. We have an output that is quite comprehensive and maximizes the number of verifiable VRPs on the internet. And every single router that is being fed by the system is going to get the exact same data. So there's also going to be uniformity in the router content. Other bonus points that this infrastructure brings is the fact that we would have less RPs on the internet if this kind of system is deployed the way that we have envisioned. Currently, there are 3,000 to 4,000 RPs on the internet, perhaps even more at this point. So there is quite a lot of traffic out there. This would reduce the traffic and increase robustness, and the convergence happens also quite fast. So the system is overall quite robust. So over here, we have an example of how robustness actually manifests in here. And the relevant, the line that represents the output of our system is again the purple line over here. And the blue line is the individual nodes, it's the output of the individual nodes. And like we see here, the blue lines often peak underneath the purple line. So what this means is that individual nodes at different points in time, as you can see here, sometimes they just have an outage for some repositories for whatever reason. These are momentary outages. They don't happen all the time, but they do happen. So on the opposite side of the fact that the individual nodes are getting sometime outages, the system as a whole remains quite stable. So the purple line remains quite stable and doesn't really peak considerably underneath its baseline. What this means is that because we have this consensus aggregation, the system as a whole is impervious to this kind of transient network failures, these things that are not systemic issues, but that happen sporadically throughout the operation of a relaying party. And this here is also another example where we have one single standalone relaying party operating and the one ByzRP instance network that we have deployed. And as we see here again, transient failures happen. These are all 24-hour measurements. Transient failures do happen, and our system is quite impervious to that. So another thing that I would like to just quickly mention is the fact that even if we have many nodes, 3, 5, 15 nodes perhaps in our network, the convergence is actually quite fast. So in most cases, it's 5 minutes or less. Could go, worst case scenario, up to 6 minutes. This is just the warming up period for all the nodes as they are being booted for the first time. And after they are reached convergence in less than 10 minutes from the first booting moment, the system remains quite stable. There are no longer moments where there are large-scale outages and things have to converge and sync again. So the system in general is, the consensus in general is quite fast and creates a lot of robustness. So summarizing, our system is quite robust. It provides safety from attacks, and it converges rather fast. So one thought that people might have looking at the content so far would be, well, should everyone at this point run their own ByzRP network?
Right. So should everyone run their own network and benefit from these sort of robustness and these sort of performance improvements? And while you could do that and you would benefit from increased robustness, where our system really shines is in a deployment scenario as we had originally envisioned it, which is that sort of a handful of operators would each run their own ByzRP node, and they would run it in a sort of global network in order to provide one global service that all network operators could use to secure their networks. And this would have the advantage that not every network operator needs to run their own relying party. This, requires additional setup. It would make it easier for RPKI to be more widely adopted because, operators will only need to point their router at this service. They wouldn't need to set up their own relying party. And because we could use a single network of these nodes to supply sort of all of these, all of the relying party functionality for the internet, we would drastically reduce the traffic to these publication points. So all the RPKI related traffic would be reduced, and this in turn also has the benefit that we could update the data more frequently. So because routers make their routing decisions based on the current information that they basically the current information that they retrieve from these RPKI objects, the more often we update, the more up-to-date these decisions are. And so to illustrate this a little bit, we sort of measured some of the numbers around the RPKI ecosystem as it is currently deployed, or rather last year when we did the study. And if we download all of these cryptographic objects from all the 64 publication points that are out there at the moment, that is about 500 megabytes of compressed data. And since we have our own publication point from which we can access the logs, we saw that in about a 24-hour period, we have around 3,000 relying parties contacting the publication point, which means that we have around 3,000 relying parties downloading 500 megabytes each. Then the sort of the validated output is at about 6 megabytes. And since the usual deployment scenario is that you have one relying party for each router, you would need to forward all this data to all of the routers. So that's about close to 2 terabytes of data for each round of this kind of validation. And we said, okay, let's say we replace all of these relying parties with just a 15 node network using ByzRP. That would cut it down by around 98%, simply because we have a lot fewer relying parties that are downloading these sort of massive cryptographic objects. That's where really the bulk of the traffic comes from. And while they do sort of exchange this information, like the validate output amongst themselves and also need to forward to the routers, that is a small fraction. And this difference becomes even more drastic if we consider future deployment. So we're kind of extrapolated roughly into the future, where we say we have full RPKI deployment. That means every network or every router has a relying party that can help the router do route origin validation. That would be around 128,000 relying parties. And if we say that every network, every prefix on the internet has an associated ROA, so a route origin announcement, then the amount of data that is spread across these publication points would increase to about 1.2 gigabytes, so a little more than doubling. And so this would result in about over 150 terabytes of traffic for every round of relying party validation. And in this case, we would reduce it even more drastically, 99% reduction if we replace all of this with a single ByzRP network. So aside from just the massive reduction in traffic, in this case, we could update 10 times as often, and we would still have just a fraction of the traffic that we would otherwise have. And you might say, okay, that's nice, but a relying party is really like a security critical component, right? Because this is the piece of software that does the cryptographic validation of the objects. Everything that comes out at the other end is no longer verifiable. So how can we, outsource this sort of security critical component to a third party and then trust that the output is still correct? So if we have this sort of global service. How can we trust this service? And this sort of ties in with what Jeff mentioned in his opening address today, basically that in a chaotic world, it's advisable to diversify, or rather to distribute. And we kind of lean right into that concept by saying that we want to distribute these different nodes across distinct entities, and then have them collaborate in a way that we don't need to trust each individual entity running these nodes or each individual node to operate completely legitimately, but we can trust that the majority does. And we do this, or we accomplish this by running a very simple consensus algorithm, which is Byzantine fault tolerant. And Byzantine fault tolerance is a concept from distributed computing. And you might have heard it in context with like blockchain technology, because there you also have a network of nodes, which is public, and you can't really trust that everyone in that network is operating fully benignly. There might be some bad apples, but you can trust that if the majority of those nodes functions benignly, then you can trust in the output of the network. And so a Byzantine fault is essentially, it covers all faults, including sort of benign failures, if a node crashes or has network issues, but it also covers like deliberate manipulation by malicious nodes or compromised nodes. And this is actually quite simple. So let's say, for example, we have a network of 3 nodes, so n is equal to 3, and we run these as a fully connected network, which means each node talks directly to every other node, so we don't rely on like broadcast mechanisms, so we know that each message arrives. And we built this on top of mutual TLS, which is essentially just a way to authenticate both the client and server. So every node runs its little web server in order to serve its output to the other nodes. And then each node sort of polls all of its peers to retrieve the current output at a given time. This can happen completely asynchronously, so you don't need to wait for the network to synchronize. Each node can sort of calculate the overall output at any given time based on what each peer currently has to offer. And then they can use the outputs from each node to independently calculate the same output in a very deterministic manner, simply by intersecting these sets. Because all of these objects are independent of each other, so we can basically just treat each of these outputs as a set and intersect these. And this is secure against F Byzantine faults, depending on how we set the threshold for this vote. So you could think of this as a slider from 0 to n-1, with n being the number of nodes. And let's say we start out all the way at 0. This is basically like calculating the union out of all of these sets. Or you could also see it as a vote, in the sense that each object needs just one vote from each of the peers in order to be included in the final output. This is sort of maximally robust and maximally resistant to censorship. So if even one of these peers votes for a given object or sees a given object, it's going to end up in the output. So this kind of also means that we're trusting every node in this network. So instead, if we move up 1, now we are resistant to 1 fault. So this is like a 2 out of 3 majority, and the final output is only going to be those objects that have been seen by at least 2 of our peers. All the way on the other end of the spectrum, we can also require that all 3 nodes, in this case, see a given object. This is complete unanimity. This is like calculating the intersection out of all of these sets, and this would be maximally resistant to poisoning. So if we consider the situation where we have some malicious nodes in this network, so let's say this one node is malicious and tries to include an object in the output that would not otherwise be there because it's not in the publication points. It's malicious. This would not be included in the final output. Even if we have 2 malicious nodes, it would not make it in this case, only with all 3. So basically, if the entire network is compromised. So this is both a trade-off between sort of robustness and trust. So if we have it all the way on the right side, in this case, we essentially lose all of the robustness guarantees, or the robustness mechanism that we introduced, but it would be most secure. On the other end of the spectrum, you need to trust the entire network, but is a lot more robust. So we opt to sort of balance these two. This is like an example with 5 nodes. Here we'd have like a 3 out of 5 vote, and this also kind of balances faster inclusion of objects. If there are new objects in publication points, then only three of these nodes need to see that before it ends up in the final output, and it balances this with faster removal. So if an object is no longer part of the publication points, then you would also need this to be reflected in the output as quickly as possible. And having this kind of majority vote balances both of these. And lastly, we can also use this very same consensus mechanism to work with these skip list entries that we had. So since our watchdog is kind of watching for malicious publication points that might run stalling or crashing attacks, and it might note these down. If we have our 15 node network and maybe one of these nodes has a problem with a given publication point, and it says, okay, that one is malicious, let's skip that one. Maybe that is a fluke, so maybe we don't want to take one node's word for it, but maybe if the majority of our nodes encounter the same problem, then we can say, okay, let's have this reflected by the entire network, let's have all of our nodes skip this. So this kind of improves performance. Not every node needs to find out for itself that this publication point is malicious. You can kind of have a consensus on which publication points are causing problems. So that's another application of this this consensus mechanism that we use in this network as well. So to summarize, what we did with ByzRP is essentially take an existing relying party implementation. We added this watchdog functionality in order to provide protection from both stalling and crashing attacks, and have this kind of adaptive skip listing where we can blacklist offending publication points. So this already increases robustness of the relying party itself. But then we put these enhanced relying parties into a network so that we process all of the RPKI information in parallel and have them coordinate in an asynchronous manner to form sort of a consensus output, which is much more robust than any individual relying party. And we do this in a Byzantine fault-tolerant manner so that we can distribute trust across multiple entities, and you can trust sort of in the majority. You can trust in the network rather than trusting any individual node. And this is also, resistant to compromise. So in case any one of these nodes or just a handful of these nodes are hacked, that also does not mean that the final output is necessarily compromised. So you'd need to compromise at least, more than half of these nodes. And the fact that we distribute this trust opens the door for running the system as a service, because anyone using it does not necessarily need to trust the individual entities that run these nodes, but trust in the majority, the same way you would do it with some blockchain networks. And if we have this sort of relying party as a service, then we could cut down on a lot of network traffic that's related to RPKI. We could update the frequency so that we have more up-to-date data that all of the networks can work with, and it would simplify RPKI adoption. So we have RPKI used more across the internet. Yeah. So in summary, using ByzRP would result in in more robustness, more performance, and hopefully also more RPKI adoption. That is our hope. And with that, we're going to conclude our talk and just quickly, point you to some references. We have the code for ByzRP open sourced on GitHub, and for anyone interested in more of the details, we refer you to the paper we published at CCS last year on the topic. Yeah, and with that, I thank you for your attention. Right. Any questions?
I guess the only information is not one and you're looking. So they want to every possible providers, but prefixes, if I run the first and the problem from RPKI is the infrastructure. This pretty much the same problem with 5 years old. There's no real reliable
backend for the whole RPKI infrastructure. And this is why you have the oscillation and all this stuff in the end of the day. So I guess the better way would be to get someone like RIPE to provide this infrastructure in a stable way that everybody can consume it, because currently it's nice that my routers, my BGP peers can say, make a forwarding decision based off signed routes or not. But in the end of the day, I still need to get this information from somewhere. So it's pretty much about every BGP peer to build up something on their own, which doesn't help with stability. So in the end of the day, it's pretty much like, yes, we need some reliable distributed infrastructure, but maybe it's up to RIPE or someone else to provide this infrastructure. Just my opinion.
Yeah.
Because else we will never get rid of route objects and we just stay with route objects.
Yeah. Do you want to comment on that? Or? Yeah, I mean, that's, yes. We basically agree.
So I had another question. So as of today, if one of these publishing points is down, right? So only the ASs that were supposed to be concerned with this publishing point will not be verifiable anymore through RPKI. They will still be routed, but they will not be verifiable. With the solution you propose, if we have 15 of these nodes that have to reach a consensus, and if you say, okay, I can tolerate, I don't know, 6 malicious or whatever, so all I have to do is to crash 9 of them to actually make the whole internet unverifiable. So have we really gained something? I mean, you see what I mean? So yes, there is this nice property of Byzantine fault tolerance and everything, but then when we look at the whole size of the internet, even 15 is not such a big number if I really want to cause havoc, right?
Yeah. So the thing is, you can one publication point that is bad, that's going to crash theoretically every single one of our nodes. But the thing is, we have the watchdog, and the watchdog works every single second possible. And if a crash happens, it immediately is going to, because it monitors the outgoing connections, detects which is the connection that caused the crash, is going to cross-reference with other nodes perhaps that experience it as well. So it's going to narrow down and avoid false positives. And then immediately it's going to reboot the relay party. So the delay would be in the seconds. And as it is rebooted, the publication points that were bad that are in this skip list, they're going to be avoided. So now the relay party reboots again. It's going to work normally. The downtime would be 1 second, 2 seconds maybe. So it's quite fast.
I don't want to attack the publishing point anymore. I'm going to attack the 15 nodes that are participating to the consensus. So if I crash the 15 of them,
they will reboot in a few seconds.
Yeah, and because they are all coming, you said it takes you 5 minutes to reach consensus the first time. So during 5 minutes, nothing happens, and I just need to crash them again. And it's only 15 minutes that I need to crash, 15 machines that I need to crash. It's not that many, right?
Yeah, that's something that was not actually on the slides specifically. So what we did is all of these nodes, they're not going to validate the publication points in the exact same order. So they're validating, they're validating different tiles in randomly chosen orders. So you might crash a couple of nodes, not the majority. They are going to detect in a matter immediately like what is causing the crash. It's going to enter the whole global skip listing of the network, and then the others are not working in that with that particular tile that has this malicious publication points. They're working with other one. There are 5 of them, so you will not be able to crash all of them at the same time.
Why not? We're not talking about accidental faults here, right?
Yeah.
These are not stochastic processes. These are intentional attacks.
Yeah.
I can launch all my attacks simultaneously against the 15 nodes.
You mean entering, but all the nodes are operating in different orders. They're not validating the exact same thing. So when an attack is detected, it's immediately propagated to everyone else who is not working in the exact same tree, saying, hey, from that point onward, bypass this particular entry.
Let's assume I cause denial of service of your 15 nodes for a long period of time. What happens? Nothing can be validated anymore, right?
Not exactly nothing can be validated, because there's going to be a short downtime, and then there's going to be rebooted, having bypassed the publication points that caused the crash. So it's going to be like immediate rehealing.
So those sets of
guess the
15, is
point-
it a dynamic set or is it a fixed set?
Which one?
The 15 that you envisage in your system, is it a fixed set that you want to have for the whole internet? Yeah.
Yes.
So
Yes.
if I crash those 15 for a long period of time, denial of service, right? So my understanding is that they will not be providing the correct information to all the other routers, then you cannot validate any of those AS association anymore, right? Did I miss something or?
Well, okay. As I understand it, you're basically suggesting that this single network becomes a central point of failure for all of the RPKI validation, right?
The 15 as a whole, yes.
Yes. It depends on how we're achieving, like crashing these nodes. So if we say that we have a malicious publication point that you're using to crash the nodes, then we essentially have, we would crash about like half of the network, let's say, and then it would, or depending on how we set the threshold, we would have, the rest of the nodes skip this offending
Yeah, I'm
publication
talking
point.
about a malicious entity because BGP,
Yeah, but then
BGP hijacks are due to malicious entities, right?
Yeah.
As opposed to classical usage of Byzantine fault tolerance, which has mostly to do with accidental fault rather than with intentional faults. So here I'm just saying, is it a good idea to use the benefits of Byzantine fault protocols by by severely increasing the threat surface, so to speak, or making it easier for a person to attack only those 15 as opposed to attacking all the other ones that we had before, even if attacking each of them individually would have been simpler. But the sheer number of them makes the attack more complicated.
Sure, but that's what we have those countermeasures for. So since we can identify the publication point that is causing the relying parties to crash,
I'm not attacking
we
the
can
publication
have
point.
we can have all of the nodes in the network skip this publication point, which means we would just be ignoring all the objects in that publication point, but they would continue to retrieve all of the other objects.
I'm not touching to the publication point. I'm just attacking the 15 nodes that participated in the consensus.
Yeah.
I crashed them, not the publication point. But maybe
No,
we can discuss it offline,
I understand what you mean. The point is, you wouldn't be able to crash all of the nodes because they react to if the publication point is the attacker, and
No, it's anyone else on the internet. Anyone can launch a DDoS attack on the internet, right?
okay. If we're assuming that we simply DDoS these nodes,
Yeah.
I think that's just a matter of adding DDoS protection. I mean, that problem is a problem that every server has, right? I mean, it's the same with the DNS system, right? You can also just DDoS the root servers, but like,
Yeah, but that's why you have Anycast, and that's why you have this huge amount of DNS servers, because we know that sometimes some of them could be attacked.
yeah, but there are only a handful of root servers, right? And essentially they're just built,
There are
you know,
hundreds-
robustly enough
there are
that they can
hundreds of
resist.
them. There are hundreds of them.
Well, I mean, we could expand this to also include, you know, several hundred of nodes, but I think that's just a matter of setting them up in a DDoS resilient manner, which I think is independent of their functionality as such. Like, I think
No,
protecting them from DDoS is like a separate problem, I guess.
it has
Sort
to
of.
do with the fault assumptions you're making. So as long as you make a fault assumption that have to do with accidental fault, this is perfect. But if you start looking at intentional faults, then, you know, the fault assumptions are different, and I don't know. But we can discuss it offline. It doesn't mean that it's not interesting. It's very interesting, right? But let's discuss it offline. Thank you.
Just
Sure.
one more thing is that we explained with the 50 nodes as a sort of an example, but you know, in practice, this wouldn't. It makes perfect sense what you said. Just 50 nodes. That's vulnerable. That's doesn't really scale up. But this could be something that is implemented by multiple different entities. So instead of everyone having their own relaying party and having to manage and patch it, and according to our studies, people simply don't patch it. 56% last year were vulnerable to known types of attacks. So in order to kind of outsource the whole thing about patching the relaying parties, this could be ByzRP could be offered as a service by multiple different entities. So could be like outsourced by different offers. It's not just one central 50 nodes. It could be multiple different like offers for such a resilient system. And you can have like different endpoints connect to different entities, service providers according to your needs.